So finally, let's take a look at one successful case study that we have done. So we did this validation case study with an Arberg machine and with a one cavity mode. The product is a simple plate. Okay. So initially we set up a process in Moldex3D using this simple interface like this, and we set up one constant injection velocity, one constant packing pressure setting, and inside Moldex3D we pass this we transferred these setting to machine interface. This is the Moldex3D machine interface, and then we can easily pass these information and set it up in the real injection machine. So as you can see, these two interfaces, they actually look almost identical. So we can easily pass the temperature setting from Moldex3D to real injection machine, and the dosage setting, the injection velocity pressure setting, and the packing pressure profile setting. All these settings can be easily transferred from Moldex3D to real life injection machine. Okay, and finally, let's take a look at the response curve on the real machine and our simulation result. So the blue curve is the experimental result, and the orange one is our simulation. So as you can see, when we look at the injection velocity versus time, we successfully capture the response time and the machine behavior that it exceed the user setting, which is 30 millimeter per second. The machine exceed the setting and slowly drop down and become stabilized and stay at 30 millimeter per second all the way to the end. And if we look at the velocity versus ramp position, the same. We can capture this delay time and the peak and the stabilized speed. And later on we can check the VP switch over here. So this is the end of velocity control, which is exactly the same as reality. Okay, and not just the time, the VP switch time. We successfully capture the VP switch time, but also we get the correct VP switch pressure value. So if we look at the VP switch point, the real injection machine gives us about 573 bar, while in our simulation the predicted pressure value is about 585 bar. So actually the difference is very, very small. It's actually lower than 5%, the difference. So we can not just capture the right VP switch point, we can capture the correct pressure value. If we look at the pressure, nozzle pressure versus ramp position, it's the same. So you can see these behavior. We properly capture all the behavior and the pressure value and the VP switch time. Okay, and then if we look at the pressure control stage after VP switch point, so over here, as you can see, after VP switch point, the pressure drops down and climb up a little bit and becomes stabilized. If we look at the orange curve, you can see there is a valley over there. It drops down, becomes lower than the setting, and then climb back up to the user's specified pressure. The blue curve is the machine, and it's the same. There is a valley. So our simulation result can successfully capture this kind of peak and valley behavior. Okay. The same if we look at pressure value versus ramp position. As you can see, our simulation result perfectly follow the experimental value. Okay, not just the response curve, but also the real part. So we have done two different short sharp parts with different VP switch point. Number one is the VP switch at 40 millimeter. Another one is VP switch at 20 millimeter RAM position. And then we overlapped the real short sharp part and our simulation result. And then we look at the overlap result. Our simulation result is exactly the same as the real short sharp part. So we can not only capture the correct machine behavior, but also with this correct machine behavior, machine response, we can perfectly capture the melt from the injection behavior. And with the correct injection behavior, with the correct flow rate prediction, with the correct pressure prediction, we will be able to get a more accurate simulation result of the final part. Okay, so let's come up to the summary for today. So when we do this machine characterization, when this machine characterization is applied to CAE's analysis, both CAE engineers and machine operators can have some benefits. For CAE engineers, the filling pattern and the packing behavior will be closer to reality. That means the predicted results will be closer to reality. We can find the potential defects of the part more easily. The analysis result will be closer to the actual production results. And for the machine operator, since the machine behavior is being considered, they don't have to concern whether this CAE analysis considered the machine behavior of their certain machine. So not just the mold design, part design, and machine, the material property, but also the machine behavior will be considered in the analysis. So the machine operator, the process engineers, they no longer have to worry about whether the machine is considered in the analysis. And also, they can understand the maximum error, the standard deviation of their machine, and they can know whether their machine is stable or not. And finally, with this kind of machine characterization service, combining our machine interface and our MMIP file, we can solve the communication issue between CAE engineers and the manufacturing machine operator. So with this machine characterization service, we can successfully consider all the key factors in an injection molding process: the mold design, part design, material properties, machine behaviors, and close the gap between simulation and reality. And after we close this gap with our software and the real machine interface, we can also close the gap between CAE engineer and process engineers. So with all these gaps being eliminated, being closed, we can finally achieve the transition from smart design to smart manufacturing. So this is what our Moldex3D machine characterization service can provide to our customers. Okay, so that is the end of this session. Thank you for your attention. I hope you enjoy it. Thank you.